guys, so in this video we are going to talk about probability, and this is in an introduction to probability. So let's look at some terminology. The first one is an event. An event is any collection of results or outcomes of a procedure. So we have simple events and then we have compound events, and we're going to start with simple events. Simple events are outcomes that you can't break down any further. So if we're talking about rolling a dice, well, we can't break that down any further than talking about, did we get a 1, did we get a 2, did we get a 3, or so on. So that would be a simple event, and we could write that as probability of rolling a 1, and I'm going to use some shorthand there. Now, if we're talking about the sum of two dice, that would be a compound event. Maybe we want to know what's the probability that the sum is equal to 3. Well, that's a compound event because we could break that down into what would be on each of the die. And we'll talk about how to solve that a little bit later. So then we're going to talk about the sample space. The sample space is the list of all possible outcomes for some kind of event that we're looking at. So if we look at the probability of rolling one die and getting a 1, we could list all of the possible outcomes this way. It's just a list of everything that could happen. We could have a 1 on the die, we could have a 2 on the die, or a 3, or a 4, or a 5, or a 6. So then to figure out that probability, it's pretty easy. It's how many ways can that happen out of the total number of possibilities. This one's a little bit more complicated because we're talking about a more complicated event. We're talking about a compound event where the sum is going to be 3. So we would need that sample space in order to figure out what that probability would be. So what would that sample space look like? Well, we could have a 1, then a 1. First die, second die. We could have a 1 on the first die and a 2 on the second die. Or a 1 on the first die and a 3 on the second die, or a 1 and then a 4. So you see how that second die is changing. 1, 5, and then 1, 6. Or we could have a 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. So you can see the pattern that's going on there. Or 2 is now what's on the first die. And then you could see down here, this would go to 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and then 6, 6. So then to answer this question, what's the probability the sum is equal to 3? How many ways can you get a 3? Well, you'd either have to have a 2 on the first die and a 1 on the second, or a 1 on the first die and a 2 on the second die. So there's 2 ways that could happen out of the 36 different possibilities there, and that would reduce to 1 out of 18. So we're going to talk a little bit more about how do we find that probability. So notation-wise, we would write it this way. I've written both of those that way, where A is the event, and what this means is it's the probability of event A occurring. So there's a couple of different ways to look at probabilities. The first one is the relative frequency approach. Now think about this, I also call this the experimental approach. So this is usually what happens in an experiment. We're going to use that relative frequency there. So how do we find that? Well, we're going to have the list of all the outcomes. Maybe we did roll that die, one die, 100 times, and we want to know what's the probability of A. Maybe we're looking for, if we roll 100 times, find the probability that we got 1 using the relative frequency approach. Well, we would just count how many times we got the number 1 out of all the rolls that we had. So your relative frequency approach is going to use what happened in your experiment. It's your experimental approach. So it's the number of times that the event happened out of the number of times the procedure was repeated. A classical approach, which is also called your theoretical approach. So in a perfect world, what should have happened? This is where you're going to use that sample space. And we said before that if we wanted the probability of 1 and we were using the classical approach, there's one way we could get a 1 out of the 6 possibilities. And that goes back to what does our sample space for that event of rolling a die look like. So your classical approach for finding the probability of event A is the number of ways that it can occur remember, we're thinking about that sample space here out of the number of different simple events. Which is how many items are in your sample space. And then we have subjective probabilities. And these, if you can't use the classical approach or your experimental approach, then usually you would have to use something subjective. That's where you're going to use information that you have to try to figure it out. For example, what if we wanted to figure out the probability that the next president would be from Alaska? Well, we've never had a president from Alaska. There's not an easy way to really compute that, but we know that the probability can't be 0 because there's people that live in Alaska that could run for president. So maybe we could figure out a way to look at how many people are eligible to run for president that would have the background out of the total number of people that are in the nation that are eligible. So it would be a little subjective here. We don't use this very often. Almost always we would use what happens in our experiment or what would happen theoretically in that sample space. Simulations. Sometimes we can't use any of those 3 approaches, so that's where we would create a simulation of some kind of procedure and see what happens in that simulation. This happens a lot when they are creating new medications. They want to know what's going to happen. Well, if it's a new medication, we don't have any information from the past, right? So we don't have any experimental stuff. That's where we would have to create simulations and figure things out. And then we have this thing called the law of large numbers. And the law of large numbers is kind of really cool because what it tells you is that the relative frequency probability, so what happens in your experiment when you roll a die 100 times, should approach what should happen theoretically. So let's demonstrate this. We're going to go into the LMS and then click on simulation websites and then go to the GeoGebra dice roller. And I'm going to take this down to, if it lets me, 1 die. So we know the probability of getting any number on here would be 1/6. So if I roll this die 10 times, you can see how everything is kind of uneven. Let's look at that probability of 1 again. Right now it would be 3 out of the 10 rolls. If I roll it 20 times, notice the 20, and I'm looking at the probability of 1. Relative frequency approach means that we would have 4 out of the 20 rolls. But if I were to roll this, lots of times, so let's write down what we're doing here. So we went 20 times. Our relative frequency approach, this would be our experiment. we have 4 out of the 20. So that reduces the 1 over 5, which is a 0.2. So the classical approach, okay, that would be from our sample space, says that if we wanted to find that probability, it should be 1 out of 6. And 1 out of 6, if I turn that into a decimal, is 0.167. So we're close to that. You can see how close those two numbers are. But we only rolled this 20 times. So what if we were to roll it? Now I'm going to change this. I'm going to keep going until I get to 100. So now we've rolled it 100 times. Still using that relative frequency approach, right? The probability of getting a 1 now is 11 out of 100. That's what our experiment says. And 11 out of 100 is 0.11. So you can see how our probability changed because we're using that relative frequency approach. But 100 is still not many times, right? So let's change it. Well, if we were to roll it, let's change this to be 10,100. So you can see now all those bars are really close to each other in height. So that relative frequency approach, we've now rolled it 10,100 times. And a relative frequency approach would be 1662. That's how many we have, right? Out of 10,100. And as a decimal, that's 0.165. So you can see we're getting closer to that classical approach. And that's all the law of large number says, is that if you were to do this over and over and over and over again, then that relative frequency is going to approach what that theoretical answer should be. So take some time and play with GeoGebra's dice simulator and see how many times it takes you to roll that. You can see that here we're pretty close with 10,100. We could keep going. And the more we do it, the closer we're going to get to that. So there's your law of large numbers.